So I'm supposed to entertain you before the most important part of the week, which is the bouillabaisse, of course. So I'm going to speak about interval exchange transformation with flips and a conjecture by Novikov. So it is not the conjecture by Novikov, okay? It's a small conjecture by Novikov. So that's why it is, I wrote A. It is a joint work with several people, Ivan Denikovich, Paul Merka, who is in the room, Olga Paris-Romaskevich, who was in the room till yesterday, and Sasha Skripchenko. And the first thing I'm going to explain is what is this conjecture by Novikov. I consider a surface contained in the torus T3, which separates T3 into two parts. So if you prefer the H2 of x is equal to 0. So we can pass to R3. So, and we have the covering by Z3. And this is X3, X hat is called a triply periodic surface for obvious reason. And the problem is very easy to ask. So if you are lost at some point, you can try to solve the conjecture because it is possible to explain the problem to kids essentially. That's why I like this problem very much because it was addressed 40 years ago, and so we have partial results, but we didn't solve the conjecture, and it is very simple. So we take foliation of R3 by parallel planes. And the question is, what can be said about the restriction of the leaves to X hat or to X? So that's the question, and a plane, to be more precise, a plane is given by the equation ax plus by plus cz equal constant, and I change the constant, and when I change the constant, I have parallel planes, and so it's given by a vector abc, and of course this vector is what is important is the projective vector. So if I multiply the vector by 2, I have the same the same foliation. So I can speak about almost every. Almost every will mean almost every direction will mean almost every ABC, so almost every AB or almost every ABC in the sphere S2. Okay, so almost every is well defined, and the conjecture by Novikov, and I think at the beginning of the 80s. Generically with respect to the measure, two situations appear. So the first one is what is called the trivial one. All trajectories are periodic. And the integrable one and so the integrable case, so there are non-bounded trajectories in R3, but they remain, all the non-periodic trajectories remain at bounded distance from a line. In X hat, yes? What?
I don't see the definition of the trajectory.
Oh, the leaves, or if you prefer, the leaves of the foliation. Okay? So now I think it's a good moment to show some pictures, so that maybe it will be a little bit. So I will not show a lot of pictures. Blah blah blah, integrable case. So integrable case is this, okay? So you have small islands which correspond to periodic trajectories, and you have some distorted lines, okay? But some more complicated stuff can happen, and this kind of stuff, and this seems to be not at bounded distance from a line, and that's what we call a chaotic situation. And the conjecture is that the chaotic situation doesn't appear generically. And so I wanted to show a third picture, which is due to Pierre Arnoux in a very different context, but for those who don't know in which context it is related to the talk by Valérie, of course, and that's the kind of stuff, this kind of picture can happen for chaotic regimes. Okay? Yes, of course. But you know it is a fractal set, so it will remain essentially the same. Okay, so that's what is a complicated picture. So this is a chaotic parameter, and I show you again the integrable case. So the integrable case, I expand it also, is this one, so you see lines and periodic trajectories. Okay, so I don't want to do illustration anymore. Tu t'occupes de ça, okay. Okay. so the conjecture is that these two cases are generic. And we will say that a vector, so the vector, I call it H. This is a trivial case, T of X. So the set of H such that we have this property is called T of X. Integrable case is E of X. And the third case, which is much more complicated, is called C of X for chaotic parameters. Is the H such that the flow in direction H on X is neither trivial nor integrable. And the conjecture is that C of X as measure 0. Okay, so that's the conjecture by Novikov. So what Anton proved exactly at that time, and in fact the conjecture was made because of the result of Anton, is that C of X has empty interior. And then Dinikov spent many years to understand what happens, and so he made a lot of progress in the direction of the conjecture. And I want to describe or to state some of his results, which are very good. So I think it is in 1990. I don't remember. A little bit before this century. And so the idea of Dinikov is to consider a family of surfaces. So to consider a function, so the idea is to consider families of surfaces. And to consider a function, E, from T3 to R, and to define M kappa, which is a level function for the energy E, because it's supposed to come from physics. The set of X such that E of X is equal to kappa. And so now we have a family of surfaces, and when we have a family of objects, it's always easier to get results than if we have only one object. So that's always what we do. And so this is a theorem by Dinikov. So we fix H is fixed, and if H is in C of M kappa, so if H is a chaotic parameter on the surface M kappa, for every other kappa prime, the dynamics is trivial. Which means that H belongs to T of M kappa. So that's a very strong result. And what it means is that if we make a small modification of M, it destroys all the infinite orbits if we are in the chaotic case. So the chaotic case is really very, very unstable. That's what it means. That's the first result. And a second result is the following. So if E is a generic function from T3 to R, there exist two functions kappa plus and kappa minus from S2 to R. There are two functions, kappa plus and kappa minus. So H, I consider H in R. And we have the property that kappa plus is larger than kappa minus. They are continuous. And kappa belongs to kappa minus kappa plus. If and only if H belongs to the integrable case or to the chaotic case. So which means that outside an interval everything is trivial, and in the interval we have either a chaotic regime or an integrable regime. And of course, if we are in this situation, in the chaotic regime, the interval is only 1 point by the previous result. So if H belongs to C of M kappa, we have kappa minus of H is equal to kappa plus of H. Okay, and so can continue here.
Can you say, I mean, how, like what does generic mean for E here?
Don't ask what is generic. I don't want to explain what okay? I don't want to answer this question. Okay, this is okay.
Yeah, no, that's, I understand.
No. I really don't want to answer this question because it is a big discussion in our paper to really write something correct. Okay, so if I denote by C of E the union of the C of M kappa for all the kappa, we see that this is contained in the set of H such that kappa minus of H is equal to kappa plus of H. Okay, so it is contained in curves which we don't understand. So that's the first thing we don't understand. What are these curves? Except in one situation, and I give an example of a function which is triply periodic, it is cosine 2 pi x1 plus cosine 2 pi x2 plus cosine 2 pi x3. Okay, so this is clearly a function which is triply periodic, but it has a symmetry, so in the sequel we will restrict to function with symmetries, and it seems that for the physical case it is the most important case, And in for me, it's the only case I am able to understand, and it will make Novikov happy because it seems that he really wants to understand this case. So in this situation, if we add 1/2 everywhere, we have the same stuff. And in the rest of the talk, I will assume that E is an even function. So this is not really an even function, but it can be made an even function easily. And in this case, it is not difficult to see, and this is really easy, to see that kappa plus, kappa minus is minus kappa plus. And thus, then I understand the curves. The curves are just constant and equal to 0. So the set where the curves are equal. Then C of E is equal C of 0, of n0. Okay, and after the work of Novikov, there is a stronger conjecture. A stronger conjecture, which is the following. We consider E from T3 to R, which is generic. Then the Hausdorff dimension of CE, of the chaotic parameters, is less than 2, which implies in particular that the measure, the two-dimensional measure of this set is equal to 0. Okay, so that's the actual version of the conjecture. And what we are able to prove, in fact, what we are able to prove is a little bit weaker, and that's exactly the definition of generic. So what we are able to prove, so everything is with these 4 people. So we are able to prove that for a generic even a function, E from T3 to R, and such that the level surfaces, so which are the M kappa, have a genus atmosphere. Then the conjecture is true. So which means that we are able to prove the conjecture in the special case, which seems to be the most interesting case, but I don't want to discuss the physical interpretation of this, but it seems that Fermi surfaces have symmetries, blah, 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 and so it seems that it is really the interesting case.
I'm sorry, I have a stupid question here about genus 3. So near maximum and minimum of the function, the levels of the surface are spheres.
Ah?
Spheres. Near max, so the function of the torus is one-dimensional, so the function
That's why there is.
near maximum,
That-
necessarily,
That,
it cannot be anything but sphere, do you agree?
yeah, that's why I less or equal to 3.
Oh, so for those levels,
Yeah.
that's what you mean.
Yeah.
For those levels which have less
So I want that there is no level with which are genus larger than 4. Yeah.
Yeah, you do not exceed.
Yeah. I don't want to exceed 3. Okay, so now I'm going to speak about something else, but I want to explain why I'm going to speak about something else, which is the other part of the title, interaction transformation with flips. So the idea, as usual, is to make coding and renormalization. Okay, that's what I want to do. And I want to explain which kind of interaction transformation with flips I'm going to consider. That's what I'm going to do now. And first, I recall a famous theorem by Keen and Maser-Vich, just to explain the difference with the case I'm going to consider. So I fix the permutation. What we know is that almost every interaction transformation with a fixed permutation is minimal and uniquely ergodic. And of course, people will tell me that I'm wrong because I have to say something on the permutation. But if the permutation is not stupid, which means then it's true. Okay. Okay, and so that's a very, very important theorem. That's the beginning of the theory of Teichmüller dynamics. And now I don't want to consider interval exchange transformation, but interval exchange transformation with flips. So what is an interval exchange transformation with flips? It is exactly the same, except that we can have flips. Okay? So I divide my interval into 3 parts, for instance, and what I do, the first one goes to the end, for instance, and instead of using a translation, I can either I use a flip. So, and I put an arrow like that. For the second one, I use a translation. And for the third one, you do what you want. There is a flip, okay? So I have 2 flips and one interval which is not flipped. That's life. And so an interval exchange transformation with flips is given by what? By the length that I will call L, the length of the interval, which is in this case L1, L2, L3, a permutation, and a vector in plus or minus 1 telling if I flip or not, and a vector epsilon, which is in this case minus 1, 1, minus 1. Okay, so that defines completely an interval exchange transformation with flips. So if you want a more formal definition, you look in the paper by Nogueira. And there is a theorem by Nogueira. That's more important. The theorem by Nogueira tells us from 1989, tells us that the situation is completely different from the previous case. And so I fix the permutation, pi is fixed, and as for interaction transformation is not a stupid permutation. Of course, epsilon is not only once, so there are flips, Otherwise, there is nothing to say. What? Different from 111. Then, and I have a measure on the L as I add for the interpolation transformation. Then, for almost every L, so I normalize the length to be 1 if you prefer. The IETF, so F, which depends on so F lambda pi epsilon as periodic orbits. And I can explain, so if it is the first time you see this result, I can explain why it is true and why it is essentially easy. Why it is essentially easy. So I make a picture and you will see that it is a proof essentially. So the picture is the following. You have small intervals and one big one, which is exchange, which is flip. Sorry. And the other one do what they want. And what I claim is that okay, so it is shift, but in the part which is in common between the interval and its image, the first half goes here and come back, and the second half do the same. Okay, so I have a periodic orbit of length 2, and in the middle is even fixed. And then, if you know renormalization, you apply Rose induction, and this is an open set. You go to this open set for almost every parameter. That's the proof. Okay, that's not more difficult than what I said. Okay, so that was just to tell you that this is not surprising that we have a different behavior. Okay, and now I want to not to come back to my problem, but to be more specific and to tell you about families of interpolation transformation, or interval transformations with flip, sorry, that will encode my Novikov problem. Yes, of course. So that's why there is a theorem. Okay, that's why there is a theorem. But that's why also I was happy to read this paper, because in 1989 it was something difficult, and now it is very simple because we know this very well. So it means that mathematics make progress, and this made me very happy. Okay, so I want to be more specific and to look at what I call CET3 and CET4, which means circle interpolation transformation, and I will describe them first with 3 and then with 4. So I pick 3 intervals on a circle, and I do the following. So for each interval, I do a flip on itself. So it is an evolution. I do it for each of interval. Okay, so that's very boring map. Okay, and I compose with a global rotation. And this is CET3. And if you do the same with 4 guys, you have CET4. And if you want, I can give, for people who are formal, I can give a more formal definition. So F L L are the lengths. You have L1, L2, and L3. FL tau of x is ci plus 1 plus ci minus x plus tau if x belongs to ci minus 1 ci and ci is the sum from j equal to 0 to I of the Lj, if you take the origin somewhere here, for instance. Okay, so you can produce formulas, but it's not interesting. It's much more interesting to look at this picture. And what I claim is that the good model for Novikov conjecture is in fact CET4. But I first want to say something about CET3 because it is a very interesting case too. Okay, so the first theorem is in both cases, if tau is different from 1/2, then FL tau is not minimal. And it works in both cases. So, and in a sense, if you believe that it will be a coding of the Novikov problem, it is exactly the same. It is another way to say that there is only one parameter for which we can have chaotic parameters. Okay, so this hyperplane really corresponds to the fact that the chaotic dynamics can only appear in codimension 1 subset. That's essentially a rephrasing of this result, but it can be proved directly, of course, on direction transformations. Okay, and so it is stronger in the sense than Nogueira's result, because Nogueira's result is, say, almost every. Here we have something of codimension 1. Okay, and now I want to understand what happens in this codimension 1 subset, and that's where I have to do separately the two cases. And 3 and 4 are, you cannot replace 3 and 4 by 5, okay? So it's really something very specific.
Can you give an intuition of why this theorem is true? Like in this picture?
1 minute. One minute. Okay, no, I can give you an intuition. Yes, I can give you an intuition. It's not a proof at all. It's just, so here, when you consider 0, it has more symmetries. And here, when we consider t equal 1/2, you have one more symmetries, so the interaction transformation is conjugate to its inverse. You really have one more symmetries than for other parameters. So that's in fact a good explanation, I think. Okay, so now what happens for 3? Okay, so the closure of f L1 half of the L, sorry, of the L, such that this map is minimal, is a fractal set called the Rosy gasket. And I will show you some picture in a minute, or in 5 minutes. 3. Essentially, it was known by Pierre, so that's why he complains, a long time ago, because the square of this map is what is called an Arnoux-Rosy. I don't want to define what it is, but there are a famous class of interval exchange transformations. And so in this case, we had essentially no work to do because it was done by Pierre and Jean-Christophe first. The first example is due to Arnoux and Yokos, and then by Arnoux and Rosy. So, as I always say in my talks, Rosy is not just the name of an induction, it was a professor in Marseille, and it was the boss of our team, and a very smart guy. So what is known for this set is that the measure is 0, the two-dimensional measure. So this is a set in 2 dimensions because we can always normalize the parameters to the total length to be 1. And we know also that the Hausdorff dimension is less than 2, and recently there were at least 6 or 8 papers about the Hausdorff dimension of this set. And I don't want to discuss this, but now it's something very fashionable, and the most recent results relate this Hausdorff dimension to affine exponents. So it was studied a lot, and so I want to answer your question a little bit better. But first, I show a picture. I show a picture if I can. So this one will go down, and then I show you at the same time the picture of the fractal in one more dimension. So I don't like technology, but it's better to show a picture than to. Okay, so that's the Rosy gasket, and in 1 minute you will see the Novikov gasket, and I'll show it to you. The Novikov gasket, it's the fractal set for in one more dimension, so it is something in R3, not in R2. This was made by Paul in a 3D printer, I think, or by Pierre, I don't remember. And you will see that this will be responsible for the same thing, but with more, for CET4. Okay, and so I show it to you once more. So you see that there is a kind of symmetry. So there are 3 parts which look the same, and there is a better definition of R than this one. So I continue on the board. The better definition is exactly to do renormalization. Thank you, Julien. Oui, j'ai fini avec le projecteur. And so the definition of of R is obtained by, so I have a map G that send L1, L2, L3. It is a continued fraction algorithm as defined by Valéry, which is L1 minus L2 minus L3, L2, L3. And I only want positive numbers, non-negative numbers, if L1 is larger than L2 plus L3. And you define it by the same condition if L2 is larger than the sum of the other two one, and the same if L3 is larger than the other two one. So this is an algorithm, okay? And we want to apply this algorithm, and at each step to have non-negative numbers. And so if I make a picture in the simplex, it is, so this is 1, 0, 0, 0, 1, 0, 0, 0, 1. It is not defined here. And the R, the definition of R is the set of L1, L2, L3 non-negative, such that Fn of L1, L2, L3 is defined for every n. So this part is forbidden. Then you do one step, you have a more forbidden part, and at the end we have a fractal set, and this fractal set is the Rosy gasket. Okay, and so I didn't want to speak about that, but Valéry mentioned rotation of TD. So what we know is that if L is in R, F L1/2 square is conjugate to rotation of T2. And so the chairman should complain because this is not true.
F the same as G?
No. F is F is a map on the, G. This F is G. Sorry. The chairman could complain because it is not true, and he is a troublemaker clearly, because this is not true, but it is almost true. It is almost true, which means that there is a measure on the Rosy gasket, and for this measure, it is true for a natural measure on the gasket, a measure of maximal entropy for the algorithm, I should say. And for this measure, almost all are conjugate to rotation of T2. But not, and which means that we are considering very special interrelation transformations, because we have a theorem by Avila and Forni, which tell us that almost every interrelation transformation is weakly mixing. So, yes? So there is a measure on the fractal, which is a nice measure on the fractal. I don't want to define it, but there is a natural measure on the fractal, and for this measure on the fractal, we have the property. What?
Rotation of T1.
It is a rotation of T2. It is a rotation of T2. It is a rotation of T2. And that's the first example is due to Pierre and Gérard in 88. It is the Rosy fractal that was shown by Valéry. No, it is a rotation of T2. That's why it is. This is absolutely a non-trivial result, and it is. It took 30 years from the paper
by Pierre and Gérard till the paper by Valérie and her co-author, and then we add so we added some stuff with Julien, Pierre, and Sébastien to get this result. So this result is not something completely easy. No, it's rotation of T2. It's really a rotation of T2. And that's the picture I showed you at the beginning. So you had this line, a very complicated line. John asked me to make it bigger, and that's what we have, in fact. So it is a rotation of T2. So no, that's not a trivial statement. And if you want me to make one more comment related to Valerie's talk, is that it is due to the fact that we have, for the induction, second Lyapunov exponent is negative. So that's a link with Valerie's talk. And so now I want to continue to the case of CET4. And then I come back to Novikov's problem.
So, Pascal, I still don't understand. What is the quality of the conjugacy?
What is the?
What is kind of, is it a homeomorphism? Because F is an interval exchange.
Yes. It is conjugate in measure. It is measurably conjugated. It is measurably conjugated to rotation of T2, of course. No, it can, and it is continuous in one direction and not continuous in the other one. So for n, so there was a theorem 1 somewhere here, and there is a theorem 2, and then the theorem 2 tells us that the set of L such that so F L 1/2, so now I am in CET4, is minimal. So the closure of this set is a fractal, which is the Novikov gasket that I show you. And what we proved is that the Hausdorff dimension of n is less than 3. So so that's why theorem 1 is true. So I state a proposition which goes from one to the other, and then if I have 1 minute, I will speak a little bit more about this n. So let E be a generic function. And even with level sets of genus at most 3. And we consider H not in chaotic parameter. Okay, there exists a gamma 0 in M naught. So I recall that it can only be chaotic on M naught that intersect all the non-compact leaves of the foliation of F, H, M naught, such that the first return map on gamma 0, it is a gamma 0, is the square of f L0 1/2, which is C belongs to CET4 and with L0 in the Novikov gasket. And that's how we relate both problems. That's how we relate both problems. So if you want to have better understanding of the Novikov gasket, then I explain something which is a variant of the induction by Arnoux and Rossi, which is the following. So I take the three parameters. So I do it for free, and you will see that. So this is the lengths are A, B, and C, and so if you want to define an induction process, it is really a kind of art. Okay, there is no way to choose the intervals, so you have to check that it works, it's very easy, and to find it, you have to be lucky. And so the claim is that, so I have these three guys, it is something in CET3, and the claim is that if I consider the first return map on f-1 of C, on the complement on the circle on S1 minus f-1 of C union C, it's the first return map belongs to CET3. It's of the same type, so I can continue inducing, and the lengths are obtained by this formula. So this is essentially what is done by Arnoux and Rossi or Arnoux and Yokos for free. And we can do the same with four guys, but it will not cover all the parameter set. We have to find another induction, and the other induction is more complicated. And is more complicated because here, if you look at the inverse of the matrix, it is a non-negative matrix, and that's what we are able to deal with. We have a second induction, which we call the negative induction, and so there is some work to do. And in the end, I would like to quote a name because it is very important to quote him. Is Fougeron. So we make some work, and in the end, we use a nice paper by Fougeron about simplicial transformations. And we apply his machinery to guarantee that the limit set of the algorithm has measure 0 and Hausdorff dimension less than maximal. So he has a very, very concrete and very powerful result. So it's very powerful because it is based on a very strong work of Avila-Guezel-Yokos. So he uses the techniques of Avila-Guezel-Yokos and had a combinatorial input. And that's how we prove our result in the end. Okay, so I think I stop here. And no, before I stop here, I was here during all the semester, and I want to thank a lot Jaredef and Nicola for the great job they did.